Welcome to Chapter 4, Hilbert Spaces. So this is my favorite part. It's very geometric. So we got a pretty good chance of visualizing things by making analogies with Rn when we're in Hilbert spaces. Section 4.1 is just a sort of paragraph of introduction. A Banach space, by definition, was a complete normed linear space. So what can you do in Banach spaces? Linear space, so we can take linear combinations of vectors. It's normed, so it induces a metric and we can measure distances. And it's complete. By definition, Cauchy sequences converge. In practice, we can do analysis. So we can do analysis in Banach spaces because they're complete. There's more structure than just completeness in a metric space sense. There's this linear space stuff as well. So you like linear spaces, you like Rn, hopefully. Hilbert spaces are complete inner product spaces. All right, complete tells you we can do analysis there as well. Inner product spaces, well, that's the idea of a dot product in sophomore linear algebra. Rn and Cn are examples of Hilbert spaces. The Euclidean norm on these spaces, the usual thing, will sum up the components of a vector squared, absolute value squared, modulus squared if we happen to use complex numbers, but sum the moduli of the squares of the components and then take a square root, usual Euclidean norm, be the scalars real or complex, as long as I put the absolute value thing there and interpret it as appropriate for complex numbers. And the inner product on Rn is simply a sum of products of the components. Let vector x have components x sub k equals 1 to n. Let vector y have components y sub k equals 1 to n. And we'll do your usual Rn type dot product. And that's an example of an inner product. If we use complex numbers, which we will, we've mentioned this in the past, it's slightly more complicated. You need a conjugate, a complex conjugate on the y's in this product, and that'll introduce the moduli when you take the dot product of a vector with itself. But conceptually, dot products allow us to measure angles. And if you can measure angles, then you can talk about orthogonality. So we can do stuff like orthonormal bases. We might want to tweak some definitions. We've looked at different ideas about bases. I think it was in chapter 2, around the end of chapter 2, and we're going to take that idea and run with it some more. We had stated a fundamental theorem of finite dimensional vector spaces. Well, guess what? There's some details to be put in. We will cover them details, and that will yield a fundamental theorem of infinite dimensional vector spaces, as I call it. And it turns out that there's only one infinite dimensional vector space. Cover that with a pretty thick layer of added details. And that one infinite dimensional vector space with a smattering of details acts very much like Rn under the Euclidean norm. So Hilbert spaces behave geometrically very much like Rn. Things you did in sophomore linear algebra, you can do them in Hilbert spaces. Well, certain kinds of Hilbert spaces. Gram-Schmidt process. We can find orthonormal bases. We can find orthonormal bases. We had talked in the past, if you maintain your idea of a Hamel basis, the same definition of basis you had in sophomore linear algebra, then that's a problem. You know that such a basis exists, but you don't know how to find it. Yeah, we'll change some things. We'll look for Schauder bases, and we will find them. And they will be orthonormal, like in Rn. So the behavior of nice Hilbert spaces is very much like the behavior of Rn. And all that sophomore linear algebra stuff can be dealt with in these infinite dimensional vector spaces. You can even represent linear transformations with matrices. They're infinite matrices if we're in infinite dimensional Hilbert spaces, but I'd almost expect that given my experience in sophomore linear algebra. one final comment. Throughout this chapter, we're going to take the scalars to be complex. It's easy enough to modify that and bust them down to real scalars. But the assumptions we'll run on will be that we're dealing with complex scalars in this chapter. And that's it for section 4.1. So welcome to Hilbert Spaces. This ought to be fun. I'll see you in 4.2. Have a nice day.